Hey everybody, welcome back to Organic Chemistry. My name is Todd Rothman, and in this video we're going to do Aromatic Systems Part 2, Section 3. So at this point we've learned about the reactions, and although it was a little bit time consuming to learn them, it's really just the beginning. Now we're going to get into the good stuff and the heart of this chapter, and that is how the different groups on benzene influence benzene to make it more or less reactive, and then in turn how do things come onto the benzene based on things that already are attached to it. And that's what we're going to learn about in the next two video sets, this section and section 4. Okay, so this section is all about the types of substituents, types of groups that are off of benzene, and we know them as being two types. There's either activators or deactivators. And we're going to learn about what they are, what that means, and then we're going to learn about how that, in turn, how does an activator or deactivator affect benzene. And we're going to talk about inductive and resonance effects. All right, so let's get started. So the first thing is, what is an activator? Well, an activator, in the simplest terms, is a substituent. Remember, substituents are things that are off the parent, off the benzene in this case. Substituent that stabilizes benzene when positive. Okay, and let me not draw a positive symbol because that's going to throw you off. You'll see in a moment. When positive. Okay, that's what an activator is. A deactivator is the opposite. Okay, deactivators, they destabilize benzene. And so they're not good, especially when they're positive, when benzene is positive. Okay? They're not good. They deactivate the benzene. They make it less reactive. Activators make benzene more reactive. It stabilizes it. Okay? Now, how do you know if you have an activator? Well, here's the two generic terms that you look for, the generic concepts. One, any atom with a lone pair except halogens. Those are all activators. So oxygen, nitrogen, not halogen, but sulfur, anything, carbon that has a lone pair, anything with a lone pair is an activator. Okay? Also, sp3 carbons, actually, let me make it more clear. Any carbon, doesn't have to be sp3, any carbon that is not partial positive or positive. Okay? Those are activators. So if you have a methyl on a benzene, it's an activator. Ethyl, activator. Alkene on a benzene, activator. As long as the carbon isn't positive, it's an activator. If an atom with a lone pair is touching benzene, it's an activator. Okay? So those, and you'll see a whole bunch of examples in a moment. Now, what are deactivators? Let's talk about that. So and you know what, let me give you two examples right now so that you can put some life to this. So let's say I have a benzene and it has an oxygen, let's say like this. You'll see why, lone pair. So the fact that benzene has a lone pair touching it, atom with a lone pair, that means it's an activator, right? Now, if I have a benzene and it has a whole bunch of carbons, this is an activator. So these are activators. So now in this case, it's not a lone pair atom, it's a carbon that is not positive. How would it be positive? Well, if it's a carbocation, no good, right? Or if it's attached to something that's electronegative, like a double bond O, then it's not going to be an activator, okay? So that's two examples of activator. Now let me show you examples of deactivators. Or let me give you the definition of deactivator. Okay, so I'll go like that. We don't need as much space, so that's fine. Okay, so for a deactivator, that's the rule. Now, what it is it's any atom that is positive or partial positive. They're deactivators. Okay, any halogen and halogens. So halogens are not positive, but they're deactivators. So either positive or partial positive, or halogen. Okay? Those are deactivators. So here's examples. If I have a benzene and I have NO2, N double bond O, O minus. Well, this is positive, right? Nitro, NO2 is positive. It's a deactivator. Okay? Now, if I have, let's say, a carbon that's positive, deactivator. This carbon that's touching benzene is positive, right? If I have, let's say, a carbonyl and then is an OCH3, okay? Well, a carbonyl, that means that this is partial positive, right? And that makes it a deactivator. So these are examples, okay? Now, notice what I did. I want you to see this because this is a very a common trick. Notice that if the oxygen is touching benzene and the carbonyl is away from it, then it's an activator. Because what is touching benzene? An atom with lone pair, activator. But look at the difference. Over here, I have a carbonyl touching the benzene, not the atom with the lone pair. See that? Oxygen's further away. Now it's a deactivator. See that? That's the key. So carbonyls are deactivators, right? Atoms with lone pairs are activators. That's the point. Now, okay, so let's talk a little bit about the influences that they have. Okay, so for example, let's talk about how substituents, how these different type of groups will affect benzene. How will it make it more or less reactive, more or less activated? Okay, and that's what we're going to talk about now. Now, it turns out that the way this works is that there are two ways to do this. There's an inductive, and that's one way. So let me just title this one more way in addition to what I wrote. So I'm going to write over here, there are two ways to either activate or deactivate benzene. And that is either inductive, A, inductive, or B, resonance. Okay, so let's talk about one at a time. So inductive is the movement, remember this from last semester, of electrons in a single, sigma, single bond. That is inductive. So if it's moving electrons in a single bond, now imagine if I have a benzene and this benzene has attached to it Z. Now, if Z was to, let's say, equal a carbon, right? So if Z is like, let's say, a methyl, then methyl is going to give electrons to benzene, but it does it through its single bond. So Z can either be pulling electrons away from benzene, like that, or it could be giving electrons to benzene like that. It really depends upon what Z is, right? And this is inductive. Notice that we're talking specifically about that single bond between benzene and Z. So let me give you an example in both directions. So here's an example of an activated and an example deactivated. Okay? And you can see the difference between the two. So for an activated, if I have a benzene and it's attached to methyl, right? Then the carbon, since it's carbon to carbon communication here between the two, this carbon will help benzene out. Methyl is going to help benzene. If the carbon that's holding methyl is positive, then it has no problem giving electrons towards benzene. So electrons move towards benzene, and that's definitely going to happen because it's a carbon. It's the same electronegativity as the benzene carbon. So it's more than happy to help out and give it electrons. Okay, that's an example. Here's an example where it wouldn't help out. So imagine if, let's say, we have a benzene and there's a nitrogen, and this nitrogen has something on it 3 times. So let's say it has methyl 3 times on it. Now, this nitrogen is positive. That's the point. This is positive, right? And now, in this case, since it's more electronegative than carbon, it's going to pull electrons away from benzene. It's not going to help benzene out. So this is deactivating the benzene, and it's doing it inductively, right? In both cases, this is inductive influence. It's through the single bond. It's not through resonance, it's through inductivity. It turns out that there are